All right, I think we can go ahead and get started if that works for you.
Are we recording this or?
Yeah, we're recording so we can share with the students that weren't able to attend.
Okay, let me quickly check if I can share my screen. Okay, how's that looking? Can you see my whole screen, Spencer?
Looks good.
Okay. Perfect. So if you guys have any question, feel free to write it down here in the chat window, right? And I'll try to answer those. Let me keep the chat window open as well here. Okay, maybe not a good idea. So if there are any questions, maybe it would be good if you guys can ask them directly here, right?
I can also monitor the chat for you.
Okay, perfect. So good evening, everyone. And my name is Ashutosh Trivedi. I'm a faculty in the Programming Languages and Verification group. And today I would really like to talk about some of the recent research that has been going on in my group, in particular on reinforcement learning and how do we make reinforcement learning more usable, more programmable, and more trustworthy, right? And that's why I'm saying here, programmatic reinforcement learning for all. It's like, how do we democratize that, bring down the cost of programming such systems, improve accessibility and stuff like that. So I gather all of you are in computer science, so you guys care deeply about developing high quality software systems, right? High quality hardware system or cyber physical systems. These systems may be used in various critical settings like safety critical scenario, could be financial critical software that you might be developing, right? Or could be security critical and so on. And you may have taken several courses like software engineering, formal methods, programming languages that talk about principled ways of developing such systems, right? But recently, what we have been seeing is a new trend in programming. More and more systems, they are software systems or hardware system. They have to deal with these components that are trained with data, right? So you see here, neural network. These are components that are trained with input-output data, and you may see learning agents kind of integrated inside the software more and more, where they are interacting. Your software is kind of interacting with the environment, and it is adapting to the changing environment. So the two key algorithms behind this, change in the way that we write software are this reinforcement learning and deep neural network. Reinforcement learning algorithms, they are these algorithms that interact with the environment, right? And observe certain reward on their action. And by looking at those rewards, they learn how to make their moves properly or how to find optimal sequence of actions. On the right side, you have this deep neural network. These are universal approximation architectures, right? Where you provide input-output data and they learn a nonlinear function out of it. And these separately, these algorithms, they have been quite powerful, but what happens when you combine them, you get something really interesting. And these algorithms are known as deep reinforcement learning that combines this power of deep learning with that of reinforcement learning. And you may have seen a lot of press for them. And kind of things that you would hear is that they have been doing everything superhuman, right? They would play Atari games better than us. They can defeat our, champions in the game of Go. And that has excited everyone, academia and industry alike. And you would see that this new kind of algorithms being more used into something which is critical for our safety. For example, this startup Wave in Cambridge, UK, they taught a car to drive itself or follow lanes within a single day without any previous, supervisory input to the algorithm. In a single day, how to follow those lanes. Now you have more and more, you would have this manufacturing, you will have robotic systems that uses reinforcement learning. For example, here I'm showing a picture of this bin picking robot by Fanuc, Japan, where this robot could sit down overnight. Sorry, can you hear me? I'm getting a feedback from someone, so maybe if your audio is on. Okay, perfect. So you would see this bin picking robot that could learn to play with themselves and learn to sort different kind of objects. And finally, there was this beautiful Nature article from Google, where they used deep reinforcement learning to solve one of the most challenging problem in chip designing. This is chip placement problem, which used to be one of the last things that humans were good at in designing chips. And apparently reinforcement learning can do that. So the key way that we have been using reinforcement learning or deep reinforcement learning in designing our systems come in two flavors. The first one is this program synthesis kind of problem, where a user design a system, right, and leave some of the crucial inputs for the reinforcement learning agent to fill. Reinforcement learning agent interacts with the environment in episodic fashion while maximizing the reward and computes, the optimal behavior. And the second kind of setting, so roughly this is like offline learning and online reinforcement learning. The online one, which runs reinforcement learning, so to say, on job, and it continues to adapt itself, as the environment is changing. So let's take some of the example to get to understand this better. Right, this is a very simple example of offline reinforcement learning, where you have this very simple problem of a one-dimensional grid world. You have, a bunch of cells. You start from one of the cells, and your goal is to reach the green cell, and you have two actions in each of the cell. Maybe in the even ones, those actions, they work in one way. In the odd cells, they work in another way, right? And your goal is to try to interact with the environment and find the optimal sequence of actions to satisfy this objective. You could write the choices that are there for your reinforcement learning agent as a program. Here I'm kind of writing this as a pseudo Python program. We are writing this navigate function, which starts with some non-deterministic state. X is the current state, which is star, and it says while X is not 4, which is your goal state, it would continue to invoke this function choose, that is a call to reinforcement learner to provide the right value. And then you have this execute function, where you would call the environment and implement that action, right? And at every step, you would observe certain reward, and your goal is to, let me see. Yeah, so once you reach the final state, you would get the reward of +1, and your goal is to get that reward as soon as possible. And you could also have your environment, sampling environment given to you as a program, where parts of that might be unknown. Here, for example, flip is some probability that may not be known to you. And you would like to use reinforcement learning to help you fill this choose function. That is one of the setting, right? Let's look into another setting, which is of adaptive programming. So you may have seen various sorting algorithms, and you know that different sorting algorithms, they work, they work best with a different kind of data distribution. Like if your list is almost sorted, you would find maybe selection sort to be good. If your list is reverse sorted, you would find one kind of algorithm to be good, and so on. And in a particular environment, you would be getting, let's say, your list from a particular distribution, right? They may be used in a setting where they're almost sorted and so on. Wouldn't it be nice that if you can write an algorithm that continues to sort the list, and it adapts itself to the distribution of the list that it is seeing, right? So if you start to see more already sorted list, it would start to move to the selection sort. If you see more, reverse sorted list, it does other way, and so on, right? So you could write this adaptive sorting algorithm, which is like this multi-arm banded problem, where you are choosing bunch of arms, selection sort, quick, heap, and bubble based on how much reward you are getting, you are doing this exploitation to converge towards the best arm. That's another way to use reinforcement learning, and is in adaptive setting, right? So the goal of my group is to kind of understand different ways where reinforcement learning is being used in the programming scenarios and make that more programmatic, easy to use. In particular, you would, as these algorithms, they are, being used in more complex scenarios, you would see that the choices of agents, they could be given as a program. The environment itself could be written as a program. That could be a structured program with, different types of variables with recursion and whatnot, right? You would like to have your reward signals given as a program, right? And this reinforcement learning setting, where different components of it are given to you as a program, that we dub a programmatic reinforcement learning. Reinforcement learning where different components are programs themselves. So here is like a quick mock-up of, some of the pain points you would find in programmatic reinforcement learning in our current state of the art, right? So let's try to understand what is happening in this picture. You would have this system programmer who would like to use reinforcement learning to co-create a system. This programmer would define the environment program, and as well as it would come up with the scalar rewards for various actions of the reinforcement learning agent. What is good, what is not good, can only be expressed in terms of scalar reward signals. Then programmer is also required to be a machine learning expert, right? And he has to define various features of the environment and somehow define an interface of that with the reinforcement learning algorithm. And this interface says they are flat interfaces. You could only show what is the current state, right? And what is the current action. Programmer is also supposed to choose an appropriate approximation architecture that could be the neural network, or what is the depth of neural network, what algorithm that you would like to use. Once you have set up these two pieces, then you could automate the whole design process by using this reinforcement learning agent that interacts with the environment, looks at the reward signal, and tries to maximize those. Once your reinforcement learning algorithm has converged, you would find a policy that is essentially your completed program, and that program could be used for your traditional verification validation. So let's understand some of the problems in this approach, right? Sorry, I went back. So I would break them into three parts: usability challenges, scalability challenges, and trust-based challenges. So let's understand why the reinforcement learning in the way that we have discussed, right, is difficult to use, right? I'm sure that you could guess some of the things already. So reinforcement learning is difficult to use because your programmer is supposed to express their intent in terms of scalar reward signals, right? We humans, we don't think in terms of scalar rewards. We think in terms of high-level languages, natural languages, programming languages, but reward is the last thing that we would start naturally thinking in that context of, right? So for example, you don't know why in some particular situation, if some action is chosen, reward is 0.5, in some other it's 78 and something, right? It's very difficult. And typically programmers under huge time stress, they have to come up with the specification and reward. And that is not really, is kind of a big hindrance towards the usability. Second part of the usability picture is that this your programmer has to define a nice interface of the system to the reinforcement learning agent, right? It has to say how a particular state looks like. And that different way that you would encode these observations that could change the performance of learning algorithm completely. For example, if you have multiple, if you have a stack in the program, if you have a queue in the program, if you have some particular structure, how do we take all of that and represent it as a string of the state? Then choosing approximation architecture is requires human ingenuity in applying reinforcement learning. Next set of challenges, they come from scalability challenges. In particular, as we mentioned that now these programs, they are given to you, I mean, the simulation and the rewards, they are all programs. And these programs, they have the structure inside, they have modularity inside, right? Once we would provide an interface to the reinforcement learning agent, all of that modularity essentially disappears, right? So, and that cannot be used by the reinforcement learning agent towards scalability. Can we do something better? Finally, we have the problem of trust because we have no explicit specification. We may have the problem of garbage in, garbage out. We somehow thought that certain scalar rewards does make sense, but we do not know exactly what those rewards mean in real life, right? So because you don't have any clear specification for the system, right? So you do not know if they are correct or the intended one. So same way, when you come up with feature selection, that brings also some of the how to say approximation in this whole framework. Finally, because you don't have any specification, you cannot apply powerful verification program analysis approaches to prove that your system that you have synthesized is correct, right? So the research in my group is focusing on principled methodologies and powerful tools coming from programming languages and verification to improve the usability, scalability, and trustworthiness of programmatic reinforcement learning. So here is some of the work that we have been doing towards the usability. My PhD student, Mateo Perez, is looking into programming languages for rewards. He's looking into different logical specifications or logical languages that you could use to specify your learning requirements and how to automatically compile those inside the reward signal. Taylor Doman is another student of mine who is looking into how do we do inverse reinforcement learning based on some of the work from automata theory and logic. John Comp is he is full-time senior researcher with Medtronic, and he has been looking into real-time applications of reinforcement learning, in particular in developing medical devices like pacemakers. With Matteo, we have been looking into also how do we kind of bring some of the structure, programmatic structure directly as a first-class citizen inside reinforcement learning. So today I will talk about this recursive reinforcement learning algorithm that kind of extend reinforcement learning from standard MDP to go beyond to MDPs with, stacks or context-free grammars and so on. There is some other work going on with respect to continuous space inverse reinforcement learning, regular reinforcement learning. We have also been looking into various developing approaches to prove trustworthiness of the systems. In particular, Vishnu Murli is looking into safety verification for cyber physical systems. My previous PhD student, Saeed, has done a lot of work, nice work in security. We have been working with Tianhan on extending some of the work. Today, I would talk about, maybe touch upon briefly some of our recent work in IC, SE on fairness. How do we prove fairness for, AI-based systems, if we get some time. So here is the rough outline of what is going to happen now. Next, we will take one of the portion from usability and talk about programming languages for rewards and why, it is difficult to directly write the rewards in some cases and where formal languages could be useful. In the second part, we would talk about scalability and discuss recursive reinforcement learning, that is reinforcement learning for structured environments. And finally, we could touch upon trustworthiness, that is how do we configure machine learning libraries so that so that we minimize bias and discrimination. Any questions so far before we can go to the technical part? Sorry, are there any questions? Perfect. Okay, so let's look into how do we improve usability by providing formal languages, by allowing formal languages to express the rewards and what is the real use of those, really, right? So before we do that, let's understand again what is reinforcement learning for those of us who may have not seen it, right? So here is like a cute diagram of reinforcement learning. So reinforcement learning is this sampling-based approach to optimization where in uncertain and unknown environments, right? So you are given an agent, you're given an environment that is not known to you completely, and that could be stochastic, right? And this agent is making some choices on the environment. And for those, he's receiving some of the rewards or grading for his actions. And his goal is to maximize those rewards and in the hope to maximize the intended objective that is coming from the programmer. Let's take a more concrete example. So here we have this 4x4 grid of frozen lake. So you assume that this is like a frozen lake, red parts inside, there are holes inside that lake, everything else is icy, and you're starting from location 0 and you want to reach location 15, right? And you have 4 choices, let's say. Either you could choose the south action, north, east, or west action. And these actions are not perfect. When you take one of those actions, because of the slipperiness in the ice or something else, right? You can move to adjacent cells as well. And you do not know exactly what are those probabilities. So to learn the optimal behavior starting from, let's say, location 0 over here, you want to go to 15. You want to start from there and kind of make a bunch of choices. Some of them would be good, some of them would be bad. And you would like to make your choices in such a way that you converge towards the optimal behavior, right? So reinforcement learning agent would choose an action. Let's take the situation where in the state 9, and you are from there, you are choosing the south action, right? With some probability, you could go to the cell 8 as well, and cell 8 is safe, you get the reward of 0 there. And from that cell, you would choose maybe next action, and let's say you chose south again. And with that, you may go into the hole in the ice, and you observe the current state as 12, and you get really this high penalty -10, right? And that was a bad sequence of action essentially. So how do we solve this problem? There are 2 flavors of reinforcement learning, right? The first one is known as this model-based reinforcement learning, where essentially you want to first come up with a nice model of the environment, continue to sample different state and action, and construct a model in the form of this Markov decision process, which is like a stochastic graph, right? Once you have this graph, you would like to kind of take that graph and solve the problem by using some of the well-known approaches like value iteration, linear programming, and so on. Other way to do reinforcement learning is this model-free reinforcement learning, where reinforcement learning agent is not trying to learn the whole environment. It's trying to learn the minimum information to construct the optimal policy. And this minimum information is the following, right? From every state and every action, what is the goodness of that action last time you took? And as you're making those interactions with the environment, you would keep on kind of modifying the values. There is this nice dynamic programming based algorithm that allows you to update your values as you're making the interaction. The good thing about model-free reinforcement learning is that it's asymptotically space efficient, is kind of uses fewer space. And a second interesting part here is because the only thing that you are storing is this, tabular information that could be stored in the form of neural network as well. And you get this nice deep reinforcement learning framework there. So coming back to the reinforcement learning problem, right? Reinforcement learning is what I call programming with scalar rewards, right? So let's think about it, right? One way to think about reinforcement learning is it's like a programming problem where the whole act of programming reduces to specifying what are the rewards, right? As long as you can express your intent in terms of scalar rewards, you have this automatic algorithm that would continue to play with itself and would find a policy that indeed maximizes those objectives, right? So it's something very similar to how you train your dog. If you are trying to come up with very complex action like bang or something where dog falls down and pretend to be dead, it's very difficult to directly tell the dog to do that, right? You have to think of like a simple small actions that you could rewardify such that the combination of those actions would give you the desired objective. It's exactly the same with reinforcement learning. But programming should be better. Programming should work for humans. It should allow us to express our thoughts. Let's see what are the problems with current approach. So some of the rewards, they are quite easy, as we have seen in this case, right? We know that red cells are really bad. Give -1 reward for that. Some of them are really good. I will give +1. Some of them are neutral, right? So I will give either 0 or -1 there, right? This was easy because we have this reach green state while avoiding going inside the red states. But some other, they are kind of notoriously difficult. So let's look into this example. It's again a grid world. You're given 4 different grids here, right? And you could just try to understand what is happening over there, right? You have 4 different grids, triangular one. You start from the grid 0. You could choose an action A and you can go to grid 3, choose an action C, you can come back. And then let's say green grids, they are good. Blue grid is bad. So you want to avoid going inside the blue grid, right? And you want to make sure that you are seeing green grids infinitely often. And that is your specification, right? Always avoid blue and infinitely often visit green. You could express this in formal logic, right? Formal logics, they allow you to unambiguously say something. There are no 2 different meanings of what you are saying, right? It's not like, what is that ambiguous statement? Time flies like an arrow, fruit flies like a banana, right? So you want to say something and you want to have only one interpretation for that. And that's what you could do with logic. So here we are using linear temporal logic, and that says globally not B and globally eventually, that is infinitely often good, right? And a good thing about this logic, LTL, is that that could be compiled into an automata-like structure, right? So think of this as a monitor automata, right? And you are monitoring the traces of your Markov decision process over that, right? And how those traces, they look like, they would say, what is the current state? Is it good or bad, right? So it could be good and not bad. And then you would take the self loop over there on the safe state and so on. Quickly, you want to check that this automaton is exactly capturing my behavior, right? In particular, if you ever see a B labeled state, you would go to trap, and from there is nothing to accept. And I would say that all of those traces are accepting that would see this green dotted arrow infinitely often, right? So in order to be accepting, you want to see B states never, and you want to see a good state infinitely often. That's roughly how you would read it here. Now let's see, how do we use LTL in reinforcement learning? You have your environment. Let's write environment in a more friendly fashion. As an MDP is exactly the same. The key problem here is that you have this programmer who has this formal specification in mind and want to use that specification, right, to give reward to the reinforcement learning agent. Reinforcement learning agent would start from the initial state, let's say yellow, and then would see maybe green, yellow, green, yellow, green, and that would form a trace. And you can take that trace and run on your automaton, right? So yellow is like neither green nor blue, right? So you will keep on taking the bottom part of the loop, not green, not blue, and then you would see a green and not blue, and then kind of continue in that fashion. So if you see 0303 trace forever, you would see the green dotted arrow infinitely often, and that is good, right? So you want to kind of come up with the specification that does that. So how do we use that in formal reinforcement learning? Again, there are 2 flavors of that: model-based reinforcement learning, model-free. In model-based reinforcement learning, you would get your system as an MDP. You would learn it really well. Once you have learned your system, you have your specification, you could do what is known as the synchronous product of these 2 machines, really, right? And inside this product of the machine, what you want to do is find a policy that sees those green edges infinitely often. It's, even if you haven't seen these objects before, it should be very easy to see, verify what is happening over here, right? So take my words for it that you have a product of these 2 automata. You start from the 0 state, which is safe. If you choose an action if you choose your action in such a way that you see green action infinitely often, you are doing something good. So in this case, you can say A and C. If I would take that forever, I would see green dotted arrow infinitely often. And that is essentially the same policy that we have looked before, which is not going to the bad state and infinitely often seeing the green state. There is another choice here also. If you choose a B action, with some probability, you can go to unsafe state there, right? So it should be clear to you that the optimal policy is from the 0 state, choose an A, and then get back with a C action and do that forever. Model-free reinforcement learning is another technique, right, where you don't want to compute the whole environment. Is there any question? Spencer?
Hey, Ashutosh, quickly, if you can go back to that previous slide, I'm curious, are we just like, we're really risk adverse to the non-safe state? It seems to me that like with enough iterations, it makes sense to take BD as many times as it takes to finally get to 2G, so we can take E as like a iterable time state, like you're getting 4 for every 2 steps instead of 3 for every 2 steps.
The problem with that, I mean, is like the way that you define specification. Think of this really, right? The bad state could be like your robot is lost in a frozen, in a lake or something, right? You don't want those states. So it's like B is essentially really bad for the life of your, system.
Okay. B is my car killing somebody. Okay.
Example.
In the extreme, right? Yeah.
Right.
Okay. Thanks.
Right. So in that case, and good is something like, your car is, I don't know, working fine infinitely often or whatever it is. We can come up with a good interpretation for that. But roughly, yeah, you don't want to see, you don't want to go to trap state, or you don't want to see the blue state ever. Right?
Okay. Gotcha. So that like D,
I mean, if possible, if it is not possible,
really exist.
Right. If it is not possible, then you would essentially try to maximize the probability of that behavior, right?
Okay, understood. Thanks.
Okay, second way to do the same would be model-free reinforcement learning. There have been several attempts, and it's a particularly tricky problem to provide rewards. Is shown by a bunch of attempts before our work that have been incorrect. So let's look into those really and see why there are intuitive ways to give rewards and why they are incorrect. So here, what you would like to do is you don't have the environment as a model of that, right? So you cannot take the product. All you have to do is provide rewards to the reinforcement learning agent, right? And what could be a good reward? What is more intuitive here is that as you are seeing the trace of your system, every time you would see this green transition, the green dotted transition, you would give a reward of 1. If you don't see, you give a reward of 0, right? And that makes a quite intuitive sense that green is something good happening essentially. So every time that happens, I would give a positive reward. And that has been like the way that people give reward in the past, but I will quickly show you that why that is incorrect. And that essentially shows how tricky it is to think in the language of rewards directly, right? So let's take the simple example. Again, the same example before, right? I cannot find my... I lost my pointer. Anyway, so let me go back. Yeah, let's take this picture really, right? So what you have done is you have provided a reward of 1 unit with every this green dotted transition, right? In doing so, you have reduced the problem of your logical specification maximization to that of average maximization. Take my word for that for now, right? And what is the average, optimal average in this case? If you choose A and C, you would get reward of 0, reward of 1, 0, 1, 0, 1. So the average of that behavior would be 0.5, right? If you choose an action B with probability P, the optimal thing would be to take the self loop there. So with probability P, you would see 1 unit of reward every time. With 1 minus P, you would not see any reward, right? So expected reward, average reward for that case would be P, right? And you could see that why the reduction is incorrect, right? you would see that if you have any value of P, which is more than half, right, you would find it useful to take action B instead of action A, right? Because that would have a higher average. And that kind of essentially shows that this reward is not capturing what we had in mind. What we had in mind is to see good state infinitely often without even thinking about with what frequency we are choosing that, right? So this particular way of giving reward is simply incorrect, right? You go back to the previous example that we have shown, the triangular one, where we are saying every time something good happens, you give a reward of 1. Every time bad happens, you give a reward of -1. But then this example shows that that is not the right reward to give. We have kind of shown algorithm that kind of formally. So we have given another way to define the rewards that is formally correct, right? And it's like a slight subtle change here. So what we do is we introduce a new sync state, and from every accepting transition with probability 1 minus zeta, we redirect to the sync. With zeta, we would continue. And we would do that for every accepting transition, right? Now notice in this particular graph, the probability of reaching the probability or the policy that maximizes the probability to reach the sync is exactly the policy that would maximize your logic-based behavior, right? And I could give you some of the other reasons why that is happening quickly, right? So, but the result is quite elegant here, right? So that says that if you can satisfy your LTL objective with probability 1, any value of zeta is going to give you, optimal policy for reachability is same thing as optimal policy over there. And that allows you essentially to reduce the logic-based problem to reward-based maximization problem, right? And the reason it is correct is I could quickly mention here that if you are in an end component of your MDP, which is a good end component, accepting, that has a green dot over there, the probability of satisfying the logical specification is 1. On the right-hand side, you could notice that if you would stay in that component, eventually you would leak out to the, sync state, and you could satisfy the reachability with probability 1. So these are equal. If you think about the bad end components, the probability of satisfaction of the logical specification is 0. On the right side, you have no transition going to sync because there is no accepting transition. So this is 0 as well. The only approximation is from transients, and the effect of transient could be minimized if you choose really large value of zeta, right? So that's the kind of a key theorem there, that there exists a value of zeta such that for every value of zeta before that, larger than that, optimal policy for reachability is same thing as optimal policy for a logical specification. And this result essentially allows us to mimic that in a model-free setting also, right? Every time your interpreter is observing the sequence of actions by the reinforcement learner, you would see a green transition. Instead of just giving a reward of 1, you would toss a zeta biased coin. And if it comes head, then you would give the reward and stop the whole episode. Or if it comes tail, you would continue, right? And in this way, you would mimic exactly the reachability-based reduction that we mentioned before. We have found this particular approach to be quite effective in, computing the optimal policy. This has been implemented in a tool, open source tool that we have been working on. It's called MongoJerry, that kind of takes your MDP in a formal language, popular language to define Markov decision processes called Prism. You could specify your specification in another popular language, it's known as HOA format, or you could directly write in logic. And we have this OpenAI gym kind of interface between the programmer and the reinforcement learning agent. We have shown the effectiveness of this reduction on a lot of small examples. And these are like interesting examples from software verification or system verification setting. So here, let me see how much time we have. 20 minutes or so. So here I would quickly talk about some of the other work that we have been doing here, right? So we have been looking into, because these are automata-based rewards, these are quite sparse. So you would get reward only once in a while, right? Can you use the automata to densify those rewards, right? We have been looking into how to make reinforcement learning more effective in this context by making rewards more dense. We have been also considering multiplayer games where you have more than one player or more than one agent choosing the action, and their choices could be adversarial with respect to each other. One is trying to maximize some property, other is trying to, minimize the probability of that property, right? So can you come up with this min-max optimal policy there using reinforcement learning? We have been looking into richer models of the environment, including continuous space Markov decision processes. We have been looking into real-time Markov decision processes and continuous time MDPs as well. Finally, we have been also working on looking into more expressive specifications that go beyond your LTL. So in particular, we have looked into this temporal logic or the timed logic called event-triggered duration calculus or time-triggered duration calculus for real-time reinforcement learning. We have also some work with Taylor on how do we infer reward machine from environment using algorithms like L-star. And in a recent paper, we have extended this specification to more context-free specifications like, context-free grammars. Okay, any questions about the first part? Good. So let's look into the second part I'm super excited about, really. All right. This is from our recent NeurIPS paper, where we have introduced reinforcement learning for recursive Markov decision processes, right? And is the first time a convergent reinforcement learning has been proposed for an infinite state Markov decision process, which has been expressed as a recursive Markov decision process, right? This also kind of generalizes some of our previous work on branching MDPs. Let's talk about these things. So here is kind of a very simple mock-up of an example that shows why you would need to encode sometime infinite state MDPs, right? Here is a cloud computing scenario where you have some task T, and you have this choice essentially, whether I take this whole task and execute it on some server, or I can break into 3 simple tasks and then execute them, right? So either you could run it monolithically and you will spend 8 time unit. There's a question here. Can you read that? Because I cannot find my pointer. Is there any question for me or no?
It looks like somebody just had to jump off. They'll check the video later.
Yeah. Cheers. So other choice could be that you want to decompose that task into 3 different tasks. You pay some price for decomposition, but then these 3 different tasks, they could be independently, allocated on the different machines. And you can take this task, either you could run on an unreliable server, right, with some probability that could crash and you have to run that again, or you could work it on a reliable server that takes more time, but then that process could be interrupted when a higher priority task arrives, and that higher priority task themselves could be interrupted when even higher priority tasks arrive, and so on, right? And you have potentially no bound on how many interrupts you could have. Now let's look into this situation where number of processes present in the system at any point in time, that would be your state. And there is a priori no bound on number of states that you could have on the system. Right? So you could not solve this problem using the older approaches of finite state MDP. Here, this is quite another way to write the same system would be using this generalization of stochastic context-free grammar, where you're saying, if I have an object of kind T and I would choose an action A1, I could give rise to 3 different processes of type S and so on. So these are known as branching Markov decision processes, right? And there is a nice story behind them. Corresponding Markov chain version of that has been studied for a long time. These are these branching processes, and they were typically in the past, they were proposed for learning by certain aristocratic surnames, they go extinct and so on, right? More recently, Kusha, Etesami, and Yannakakis, they have studied this for optimization in games. So let's see what is the problem. You are given this recursive branching Markov decision process. There is a graphical way to write the same thing over here on the right, and you might want to notice that it is very similar to your MDP, but with a slight difference here, right? You could choose, you have this non-deterministic transition. You could choose, either action A1 or A2. You have probabilistic transitions, like from S with probability. If you choose A2 with probability 0.4, you can come back to S and so on. But then in addition to that, you have this branching transitions as well that are shown with this orange dot, which gives rise to 3 different instances of the next process. You start with a single T and you choose an action A, you end up with 3 S's, right? And so on. So your goal here is, the optimization problem of interest in this setting is that of finding a policy that maximizes or minimizes your cost. In this case, we want to minimize cost to termination. When the model is completely known to you, right, and all of the rewards, they are strictly positive with some kind of assumption, you could reduce this problem to solve this Bellman optimality equations, right? And you could take this equation, write a linear program and solve those. Quite nice. But when model is not known, there is a challenge. It's exactly the reinforcement learning problem. So you have some task T, you choose an action A, you do not know what would be the evolution of that, right? And that is not known, and you will learn that by sampling. So you will choose some particular action, you would get 3 processes, and that could be one of the sample, right? The key challenges in this that kind of distinguishes from the previous work is that the state space of this MDP is infinite now, right? Number 2, one-step reward that is assumed to be bounded in the standard MDP setting. Here it could be unbounded, and there is no discounting in the reward, and that provides extra challenges because there is no contraction. We have proposed a model-free reinforcement learning algorithm for such systems, and we have provided convergence guarantees under mile assumption, and we have implemented this inside the tool that we have been developing, Mango-Jerry. I just want to quickly show the main result. Here is the rough mock-up of Q-learning for finite state MDPs. The typical convergence algorithm is the following, that says that if you choose your learning rates in a particular fashion, and you would sample every state action infinitely often, your sampled values, they would converge towards the optimal values. In our setting, what we have shown is that as long as you would choose every state and action pair with certain minimum probability, right, the optimal values would converge, sampled values would converge towards the optimal one. So yeah, this is kind of a very beautiful generalization of something from finite states to a system with infinite state. In a recent work, we generalized this model a bit more and looked into this general class of recursive Markov decision processes. Here is kind of one of the example of what this recursive MDPs they look like. So you are given these functions, right? These are, each of these function could be considered as a Markov decision process, right? That these functions, they could call other functions. Those are MDPs in itself. They could return different values and so on. Graphically, you could plot it as the picture shown below. You have 3 different MDPs, T, S, and H. An MDP T, if you're in the state U1, you could call the MDP S, right? And you can go inside that MDP. So for example, if you call from U1, go inside B1, you would come back to the location U3. And on the stack, you would remember where you were in the previous function. And as you would continue, you have a stack of the previous calls of the system, right? And you are observing the rewards and everything, right? And return values and whatnot. So you could see how this looks like exactly your recursive programs or programs with, calls and returns. So we call these systems recursive Markov decision processes, and they generalize essentially your MDPs with the power to call different functions and return certain values inside. So I would just quickly declare what is the key result that we have obtained. We have shown that if you have we have given a tabular recursive queue learning algorithm and provided convergence guarantees as long as you have a deterministic MDP, or if you have a non-deterministic or stochastic MDP, but they have only single exit in each of them, right? In addition to that, for the general case, we have given deep learning algorithm that is more sensitive towards the structure of the system, and hence it is able to scale better than other state-of-the-art algorithms. These results and everything else that I have introduced earlier has been implemented in this open source tool. So if you are trying to kind of play with some of these ideas, go and download the tool, and if you have some interesting ideas, come and discuss with us. Finally, I have this little kangaroo here that I could press and jump to the last of the slide. So we'll have like 5 minutes or so. If you have any questions about everything that we have seen so far, I'll take them now. Okay. So in this last thrust, we have been looking into how do we improve trust in AI-based software systems. And this is some of the really interesting work that we have been doing with my ex-PhD student, Saeed Tisbaz-Niari, who is a faculty now at UT El Paso. So in our work in ICSI this year, we looked into how do we configure machine learning libraries so as to minimize discrimination inside the training of those neural networks. We have been looking also in legal critical software, which is this text preparation software, and try to understand what is the notion of specification in such software systems, right? So if you have, let's say, a normal program, you know what is a specification. You don't want to divide something by 0 and so on. But if you have a legal critical system, when you are putting a particular user that is getting some value, what is the meaning of correctness in that sense, right? It's a very interesting problem. And it's also known as, in software engineering context, the oracle problem, right? You do not know what is the ideal answer to a particular input. And that makes it quite challenging to pose even how do we specify the properties for a legal critical system. On the other hand, our US law is based on the common law system. And we have this, what is known in Latin as, stare decisis. What does that mean? Is that if something has been decided, you may want to kind of claim, if your case is something similar, you should get the similar verdict as well. And that gives a hint towards what kind of specifications would be useful for legal systems, right? And these are what we call this metamorphic specifications, where you would say, I do not know exactly what is the right value for this user, but if there is another user which is similar to this user, their verdict should be similar as well, right? There is some other work that I would skip right now and go to the next slide. Here is like what we have been doing right now in different directions is like improving usability, scalability, and trust. And our goal is to really make reinforcement learning as easy and as accessible as writing a Python or Scratch program. And in fact, that's what we are doing. We have some recent funding to introduce reinforcement learning within some of the tools that children use to program, right? So we are trying to understand what could be a good, interaction with the human programmer and reinforcement learner in a way that even children would learn to interact with these reinforcement learning agents. I have been looking, so we have some pretty exciting work ahead in front of us in developing some of the summer camps. If you're interested in all of these translation activities of research, right? Please come and meet me. We are working on, summer camp for K-12 students to teach them programming with reinforcement learning. Some of those ideas would be translated towards teacher development, professional development workshop for teachers around this area. And finally, we have also this nice pre-collegiate program where we could attract some of the students who traditionally do not go to colleges, right? And make them excited in particular computer science and kind of computer science that we do these days. Finally, I would like to thank all of the funding agencies here, and we received some nice fundings from these guys, really. And here is the acknowledgement of my PhD advisees, other student collaborators, and faculty collaborators. So here is a picture for my webpage and my group's website. If you're interested, reach out to us, look into what others, faculty members are doing in our group, and talk to us. You know where to find us. Yes, Spencer.
Awesome. Thanks, Ashutosh. What's your preferred way for us to get in contact with you? Email, break into the PLV lab?
Email is good.
Cool.
You know how the email structure works there. It's ashutosh.trivedi@Colorado.
Thank you.
And yeah, set up a time because our lab is kind of closed all the time to minimize distraction for our students, right? So you send us an email and find some time.
Awesome. Thank you.
Other questions? Okay, so let me just stop sharing here. Then.
Yes, thank you for your talk. I had a question.
Yeah, go ahead.
It seemed like that you were interested in making reinforcement learning more programmatic in an educational setting.
Mm-hmm.
Did you have any interest in like prototyping reinforcement learning systems, or is it or is this programmatic educational prototyping? I mean, I'm sorry. Or is this more programmatic Scratch type setting primarily for education?
So we have been working on this tool that has been open source, MongoJerry, right? And we have been pushing most of our research inside the tool, but that is very researchy right now, right? So it's just a prototype. So we have all of the reward language compilation framework inside. We have the recursive environment. How do we express? But it's not really user friendly, right? And indeed, we have interest in trying to kind of make it more friendly, looking into Python-like interfaces for those. And I think that work could be, if someone is interested, we would like to pursue that work as well, right? So like develop the front end with Python that kind of inserts your reinforcement learning agents inside the compilers themselves. I don't know if that answered your question, James.
I think so, yes.
Okay, yeah, but I think this is interesting, really, right? So in particular, there is something exciting about reinforcement learning, right? That even children should use, even though they are doing, this is very controversial topic. You would say, while if someone is trying to learn the program, why we have to give them reinforcement learning? But then I would say that it's somehow, programming is essentially, it kind of, we as we go forward, we keep on improving the abstraction of programming, right? We were doing, maybe more low-level programming, then we go high-level programming, and even higher-level programming would be just to mention what you want, and your compiler automatically gives you that, right? So reinforcement learning essentially is bringing another abstraction to us, where you could do this like a semi, declarative programming, where you would write your intent in the logic, and you just press the button, and your whole job as a programmer is to say what you want, and reinforcement learning agent would create that for you. This makes sense, James?
Yeah, it does.
Yeah. Rishikesh, go ahead.
Yeah. Hi, Ashutosh. My question is most of a technical term. I was just
Mhm.
reading your recursive reinforcement learning paper. The reinforcement learning is based on Markov process, right? So
Mhm.
all of your recursive reinforcement learning is also depend on Markov process. Like the now current
Right. Right.
previous state is dependent on the current state, something like that.
Mhm. You could think of Markov decision processes extended by the power of calling and returning different Markov decision process, right? So you could think of like you can do a function call, and where the function that you're calling itself is a Markov decision process. Is
Okay,
that-
and
yeah.
yeah, and how do you see like right now? I can just see that you call a function which is previous function you have been calling, right? Like
Mhm.
suppose there are two states, successive states. The
Yeah.
recursive function just works on the successive states, right now, currently, right?
Sorry, say that again.
If there are two states,
Mhm.
your research, from what I'm getting, is like using your recursive function is using only the two current two successive states. Is not taking what you can say.
Let me share my screen. I think that could be a good point to make here, right? No,
Yeah,
right? So, I mean, you have, let's say you are starting with this process MDPT, you're in the state U1, you chose some action, right? And then you
yeah,
reach this particular dot. That is essentially, it's saying call function S. And then you go
yeah,
to function S and you appear over here, you would do something and then maybe call action S again, which is calling itself, right? And this will come out to be the U3 state again. And maybe after certain attempts, this would get out in exit in U4, that would be coming back in the previous context. So you would have essentially your stack of contexts that you have been so far. And every time you come back from some context, you want to store whatever the state right now and continue from there. So it is like your standard, you know, what we call them, the modular programming scenario.
yeah, like a stack. Like you just from the T you are calling S, but then you are supposed to call from S to T, or you can call from S, but you can't
Right.
call from H to T. You can't call it, right?
You can call it. No, this is the powerful part, really, right?
Yeah, yeah,
Before our work, people have looked into this hierarchical setting in which there is a restriction on what you could call. We have no restriction. You can call from T to T itself. You can call from T to S and S to T in a potentially recursive fashion.
yeah. That's what my point was. Like, my question was.
Okay.
Yeah, I
Yeah,
get it.
so this goes beyond hierarchical MDPs. This is like we permit pure recursion inside, and we want reinforcement learner to find a policy that restrict that recursion and in a way that there is no infinite recursion, of course.
Yeah, get it. Got
Good.
you. Thank.
Yeah. Okay. If there are no other questions, I thank Sarah for typing my email address here, right? Reach out to me with the email address. And we are always interested in finding students with the common interest, right? Reach out to our PhD students, talk to them, and see what kind of research has been going on in my group, and in particular, other researchers with the programming languages and verification. So I think one of the things I found as a new master student, really, for you guys, right? Some other groups, they have a better advertisement, what you're getting in machine learning, what you're getting with the systems, but programming languages and verification might be something new to you, right? And essentially, I mean, what we kind of, you have to talk to us really to see what kind of research is going on, but roughly we are interested in developing programming languages and formal approaches to make sure that the systems that we are developing, they are trustworthy, right? Okay. I see no other hands. If that is the case, maybe Sarah, I'll leave you with the final words here.
Yeah, I just want to thank you for sharing with us, and thank you guys all for coming and learning. And yeah, as Ashutosh mentioned, email is the best way to reach out to him. So if you're interested in getting involved, shoot him an email. Thank you guys so much.